Welcome to today's CMCC lecture, which will be held by Professor Dargan Frierson from the University of Washington. My name is Momo Butenschön from CMCC, and I will moderate this lecture for you. But let me start with a brief introduction of CMCC, as we are hosting this lecture series. So CMCC is a foundation that is international, independent, multidisciplinary research center, and we study the interaction between climate change and society. We have a large network of international points of reference in climate change research. We have ongoing partnerships with institutions in over 70 countries. That, of course, includes the European Union, but also countries in the Mediterranean basin and Africa, as well as Asia, India, China, and also the United States, Canada, and Japan, still in Asia. Our mission is to produce advanced climate research, developing cross-cutting and multidisciplinary analysis data that combines first-class climate modeling with climate change impact modeling and environmental economics. We do that to ensure reliable, rigorous, and timely scientific results that stimulate sustainable growth, protect the environment, and develop science-driven adaptation and mitigation policies. And all that to deliver crucial scientific insights needed for a successful transition to a sustainable future. Our research activities are organized in a structure that allows the collaboration and interaction of expertise from multiple disciplines that are involved in research, but also in the decision-making processes. So we have 3 different institutes that combine climate and social science researchers from all over the world in a multidisciplinary environment. We have the Institute of Earth System Predictions that is leveraging climate modeling capabilities and turning scientific knowledge into improved predictive tools. We've got the Institute for Climate Resilience, where transdisciplinary research at the intersection of climate, ecosystems, and society is developed. And then we've got the European Institute on Economics and the Environment that evaluates sustainable and socially enhancing climate strategies at the intersection between environment, technology, and economy. Throughout our institute, we've got transversal strategic programs. Those are 4. We've got the integration of the planetary biogeochemical and industrial carbon cycle, global coast as the new frontier, predicting socioeconomic outcomes in a changing climate, and integrating AI and ML in the modeling chain. Those are the core pillars around which our research agenda is set, and they are crucial for the understanding the challenges that we are facing within socioeconomic systems and in the environment that are characterized by the changing climate. Infrastructure-wise, we've got 3 important centers. Our high-performance computing center that is enabling all the heavy workload of our climate simulations. We've got the Advanced Digital Innovation Center that is a transformative hub bringing cutting-edge technology and critical research needs to the future. And we've got the Advanced Training and Education Center that provides education, training, exchange, and knowledge transfer. So now we're coming over to our actual CMCC lecture series. This series brings some of the world's leading experts in climate and science and policy to the wider public, and they join us to give their insightful discussion of frontier topics of climate change. So today we have Dargan with us. Previously, if you're curious, we had Samantha Sidlicki, Ian Su-Wing, and Raisinger Igor Linkov, but also many others. Please use the QR code if you want to see previous lectures. And similar to the previous lectures, also this lecture will be recorded, so you will be able to go back to it afterwards. It will take some time to bring it online, but it will be available after the webinar. So Some technical things during this session, during this lecture, your audio and video are deactivated throughout, but there is the possibility to interact and to intervene and ask questions in a written form during the Q&A section. We will probably not have the time to go through all the questions, so we will select some of them, but we will go through all the questions afterwards and try to respond to them as far as possible. And with that, I hand over to our lecturer of today, Dargan. The floor is yours.
Thanks so much. It's such a great honor to be here visiting CMCC Bologna, just one of the world's leading institutes in climate modeling, analysis, and solutions. I've been here since November at the Bologna campus here, and it's additionally a great honor, kind of humbling, to be the Laura Bassi Fellow here. Laura Bassi is the first woman ever to receive a PhD in science, and first ever to be paid as a lecturer at a university as well, where she was here at Università di Bologna. So yeah, also very much want to thank my host here at CMCC, Panos Athanasiadis, who's just a brilliant scientist and a wonderful collaborator to have been working with over the past few months. So I'm going to talk about how to model the future, both in terms of climate science and interactive learning through things like video games to describe the future of the world. I think it's important to interact between art and science. And at the Museo Novecento in Firenze, there's this message on the walls that says, everything might be different. And it's open to interpretation what that means, but I think it's very important as scientists to communicate what we think are some surprises that have been happening. So I'm going to share some of those with you through the talk. One is the rapid increase in wildfires that are occurring kind of in the Arctic regions, the farthest north forests in the world. In places like Siberia and Canada have been burning really rapidly recently. Also, over the past few years, the global temperature has risen surprisingly quickly. So I'll talk about some analysis of that, why that could be happening, and how we can predict the temperature into the future. And then finally, some very good news is that solar panels are plummeting in cost, which really changes the type of solutions we can look towards in the future. I'm going to argue that solar panels are the most consistent with climate justice as well, because they can be installed on such a small scale. So first, let's talk about wildfires. This was very, very stunning to us in North America, that in 2023, in particular in Canada, there was a record-breaking year, and not just a small record. 4 times the amount of area of forest was burned as compared to any previous year. So absolutely shattered the record there. And these are some of those fires growing across British Columbia on the west side of Canada, and also in Quebec. The years 2024 and 2025 were also very extreme in Canada. So here you can see the previous years as they developed throughout the annual cycle, and that 2023 year being so anomalous as compared to previous years. Most of these fires, since they're happening far from populations, are induced by lightning. And this is an animation that was put together by a graduate student working with me, Damien Beecroft, in applied mathematics at University of Washington. The yellow dots there are lightning strikes, and then the red are fire ignitions. These lightning-induced fires. The Lightning induced means that that oftentimes these are predictable to some extent. We know how to predict the weather of thunderstorms, so having a little bit of extra time to prepare for a potential wildfire might mean, for instance, that these could be put out. Why do we care about wildfires in remote locations? Certainly for ecology, certainly for carbon emissions as well. But another reason to care about these is smoke. Air quality can be absolutely deadly in these events. This is a picture on the left of Seattle, my hometown, during a wildfire event. Often we have beautiful summers. That's the time to visit Seattle traditionally, where it's sunny and cool, not rainy like it is the rest of the year. But the wildfires recently have made it very difficult in terms of air quality. And it's not just the west part of the United States. This is an animation that shows smoke coming into New York City. So these are millions of people who are being affected by the smoke. The wildfire increase in the Arctic was not expected at all, even just a few years ago when the last round of climate models were run. So here in the plot on the right here, it's the observed change in wildfire amount in red. And that blue flat line that's so small nearby is what was put into the future climate models. So instead, in a modeling exercise by Ed Blanchard-Rigglesworth and Patricia de Repentigny, we put in the dashed line, which shows an increase in wildfire amount, because this is clearly not a steady state that we're looking at right now. The haziness of the air in high latitudes of the Arctic has increased in places like Siberia and Canada. On the plot on the left here, you can also see the decrease in aerosol pollution, particulate matter pollution over China, which has done a good job recently of decreasing their air pollution. But we put in this into a climate model. This is the CESM model from the National Center for Atmospheric Research, which unfortunately is quite possibly going to be closed down. 1,000 scientists work there in the United States, and it's currently planned to be closed by the Trump administration. We found a large cooling effect in this climate model due to the wildfires. So less rapid global warming in response to the fact that the air is so hazy with that greatly increased wildfire smoke. It's not the type of climate solution that we want to see, though, because again, this is terrible for air quality, very much slows down. It affects climate not just within the Arctic as well. The precipitation change is shown on the right here. You can see that even very, very distant in the tropics, right around the equator, there's a big shift in the rain band there. Essentially, what happens in one part of the Earth's climate does not just stay in that one part. We live in a very interconnected planet when thinking about the climate, as well as other things. These changes that happen in the Arctic are felt in places like Europe, in places like the tropical oceans and continents as well. This links to some of my previous research on ocean circulation and tropical rainfall. one of the most prominent climate features in the Atlantic Ocean is a large amount of heat transport northward within a circulation that we call the Atlantic Meridional Overturning Circulation. And although it's mostly centered in the higher latitudes, our previous research also showed that there's a tropical impact of that. So on the left here is what the precipitation looks like in a climate model, and the one on the right shows what happens if you symmetrize the Atlantic Ocean circulation. So instead of a lot of heat being brought northward, it's symmetrized, and that results in a large change in precipitation to the south. So this is the impact of ocean circulation on precipitation non-locally. With colleagues here at CMCC, we've been studying changes in this same ocean circulation. This is a plot by Domenico Giacinto here. Also Panos Athanasiadis and Dario Nicoli are collaborators on this. So this uses the CMCC climate model as well as some other ones to study the response of climate to warming from carbon dioxide and other greenhouse gases. That's shown in red. And then also due to this air pollution aerosol shown in blue. And although carbon dioxide induces a slowdown of this Atlantic circulation, which is something that could have climate impacts all over the world, it's been largely compensated so far by an acceleration induced by aerosols. This has to do with the temperature patterns that are induced by these, as well as salinity changes of the ocean. The sinking in the ocean tends to happen where the water is the most dense, which tends to be the most saline as well. So the warming induces the slowdown in the circulation, and aerosols induce an acceleration. These have largely compensated over the historical period, but it's something that could change into the future. So in collaboration with Domenico and Panos and other CMCC scientists, we've been digging into these salinity, sea ice circulation, cloud, and atmospheric energetic processes to understand those better. How have emissions changed recently? So the main precursor of air pollution from human causes are sulfur dioxide, which comes from dirty coal burning or diesel fuels. And you can see on the left here that it's actually been decreasing really substantially. So the part of the climate system that causes a cooling has been slowing, has been decreasing recently. This is very, very good for human health, but it has a warming influence on the climate on its own. Carbon dioxide, on the other hand, is the big cause of global warming, of course, and fossil fuel burning has not decreased in the recent past. In fact, despite knowing about the climate change problem for many decades now, recent years have set new records in carbon dioxide emissions. The students that I teach at University of Washington are increasingly interested in knowing about what are ways where we can decrease carbon emissions, and especially this is a time in the United States where we're not making progress on this. In fact, we're slowing progress all around the world by pursuing oil resources far, outside of our own borders. So I wanted to show y'all this book that I wrote recently that was developed for an intro course called Climate Justice and Energy Solutions. The subtitle is 100% Clean Energy for 100% of the People. So we're thinking not just about how to shift away from fossil fuels, but how to do so in an equitable way, to do this in a way where we have attention to who's been most burdened by pollution in the past. This is a free book available online, so you can look it up, or we'll post links to this as well. It's not just my perspective on climate justice, it's the perspective of climate justice groups from all around the world. From big scale farmers groups worldwide to local groups all around the world. And we're also trying to increase access to the most state-of-the-art modeling tools so that anybody can make up their own scenarios of the future. So I'll be showing some of those later. What is the future projected to be like? What's the next decade projected to be like? CMCC is one of the best institutes for making these decadal forecasts. So they show they make decadal forecasts each year that update based on the state of the ocean, state of the cryosphere, the ice in the climate system, and this in red is their prediction for the next 10 years. And you can see, in fact, that the 1.5 C threshold that's been argued by the international community almost every year in their future ensemble of forecasts is above that threshold. So there's very little chance that we'll go back down below 1.5 C. And this was particularly stunning to me when Panos and Dario showed this plot to me when I first arrived a couple months ago, that there's a non-negligible chance that we might exceed 2 degrees warming over pre-industrial within the next 2 years. There's a chance, at least in some of their ensemble members. And the initialization to the current ocean temperatures really matters for this result as well. So the blue are the uninitialized simulations, which are what are typically run by climate modeling groups. But when you do the initialization, you get a much higher chance of those higher temperature thresholds to be crossed. So it's important to understand why it is that the current conditions of the ocean are giving a much higher chance of more rapid temperature change. So again, this is something that's surprising to scientists, that this warming has been so rapid. We want to know how quickly we have to reduce emissions in order to hit a particular temperature threshold into the future. And a lot of the science on this is done with relatively simple models and in collaboration with a lot of software designers, game developers, and artists in University of Washington and around the world. We've got this group going called Earth Games that makes interactive tools or games about climate science. And this is one where basically we put in one of those state-of-the-art tools that can be run on even a phone or a laptop. It's a pretty simple set of equations. And from this interactive tool, you can reduce emissions in the electricity sector or the transportation sector or agriculture or buildings and see how the temperature thresholds are met. This is a model that, again, is used for scientific research. It's based on the FAIR model, which I'm going to talk about in the next segment of the talk here. this is something that we've done both research and outreach about as well. So FAIR stands for the Finite Amplitude Impulse Response Model, and it's used to very, very rapidly tell whether an emission scenario would keep us under a particular temperature target, like 1.5 C or 2 C. This, though, because it needs to be run so rapidly, is actually a globally averaged model. You know, a lot of the work here at CMCC involves very high resolution models that can capture features of the ocean and atmosphere that are important for climate, both regionally and globally. But this model, on the other hand, is very much on the other extreme. It is a very simple model to run. It's extremely well documented. It's open source. So all of those aspects of it have allowed our research group to examine the behavior of this model in a lot of detail. And we found actually that this model called FAIR is not matching the observed, the future projections of CO2 that are made from other models. Especially in its very newest version, it undershoots even across all of the ensemble members where you change parameters. In this model, all of them are lower than the black lines in each of these future scenarios that are considered. In order to study this, we found that in response to a pulse experiment, you know, this is a model that's supposed to be tuned to other models. We found that FAIR dissipates a pulse of CO2 much, much too quickly, and without nearly enough variance. So we're working with the team who develops this model to try to come to a solution, a new solution to fix this, basically. We found that even though this is a model where it's constrained to capture the observed CO2 change exactly, it does so in a way where most of that CO2 is in a pool in the model that has no variance, and that suppresses these other pools that do have more variance. And it's just sort of a way to study the mathematics of these models and recognize that just because it's tuned to the more sophisticated models doesn't necessarily mean that it produces an accurate simulation of that. CO2, this means, of course, that CO2 might persist for much longer than the simulations with FAIR suggest if current pulses of CO2 get dissipated into the ocean or the land in that model. So really we need more of the comprehensive models like the CMCC ESM to run emissions-driven simulations, and these are happening around. MoMA is one of the scientists who works on this, who introduced me here. So we need more emissions-driven simulations to tune these simple models. Yeah, it's an important uncertainty. It's linked to the wildfire problem that I discussed earlier, right? Because if more and more forest fires happen in the future, that's carbon that's going into the air. It's linked to the ocean circulation because the speed of these circulations result in more or less carbon dioxide going into the ocean, where it causes acidification on the one hand, but also takes it out of the atmosphere. Ultimately, the future of climate is most determined by the energy choices of the world today, right? How could emissions change into the future is the most critical question, right? And here, my surprise and excitement about this part of climate is a very, very positive story. The price of solar panels has been dropping just incredibly dramatically over the last 15 years. This is a report from the International Renewable Energy Agency that shows, factor of 6 decreases in the cost, so much cheaper than just a few years ago. Even in places like Western Washington, which is the setting of the book Twilight, where vampires live because it has the least sun in the entire United States. Even in Washington, solar power, photovoltaic power is really taking off. Microgrids are increasing worldwide, which means you don't even necessarily have to be connected to a big grid, and it gives you resilience into the future. Resilience in that even if the power lines are down, a microgrid can start back up and bring power to places, even if there's a wildfire going on, right? This is really important for resilience to climate disasters into the future. Microgrids are greatly increasing. Solar is absolutely soaring all over the world. We have them here on the roof at CMCC, right? I can see them out the window here at the Università di Bologna campus. The downside with energy, though, is that fossil fuel emissions are not decreasing right now. So what's going to be the way in which the increase in solar affordability could be leveraged to also decrease fossil fuel emissions? The traditional economic modeling of climate solutions is based on carbon pricing, but the fact that now solar is cheaper than fossil fuel sources sort of suggests that modeling might not be the only way to look at things. There is an interesting theory that's been elaborated by folks like Stephanie Kelton called modern monetary theory that suggests that, in fact, federal governments like the EU or United States can really spend as much as it wants on certain problems, with the only concern being whether the spending is inflationary or deflationary. And spending on renewables is deflationary, typically. And if care is taken that resources don't become scarce, it makes future energy costs cheaper, right? Imagine if everyone had solar panels on their roofs and electric vehicles so that you can fill up your, car or motorcycle essentially for free from the sun's rays on the roof and directly into your battery. Now, you might then need, this suggests that clean energy spending could be very large, right? But you might need direct policies, though, to phase out the fossil fuel industry, right? We might actually need the ways to, put essentially fossil fuel companies, restrict the amount of fossil fuel they can take out of the ground, right? So I'm interested in modeling more of those types of futures and contributing to that effort. We can imagine futures that are based in climate justice. They're closer than we think. This seems like a dark time for climate policy, but things could change very quickly, and it's important to be ready for those times when they become politically feasible. So with the Earth Games group, this is an app made by Dargan Frierson. We're trying to make little science-based tools in which you can create your own scenarios of the future that are, again, based in energy science and climate science here. Essentially, the two efforts are to generate electricity only with clean sources, renewables, right? And then also electrify all of the other uses of fuel within industry, buildings, transportation, right? I've also been working with the post-growth community, modeling community over the last year or so, who's looking at developing these scenarios that are more based in justice and equity. Here's another one of our little Earth Games interactive tools. This is based on a set of calculations called Decent Living with Minimum Energy. We don't have to compromise on things like poverty alleviation, right? If the very conspicuous consumptions, super yachts, private jets, things like that are limited, it gives a lot of room for sustainable development, electricity to be available for all. So there's a lot to be optimistic about this and a lot to strive for. You might be thinking that our Earth Games projects don't seem very fun. We think that it's important to bring the science to the modelers, but we're also interested in creating fun games that can teach about the climate as well. This one on the right here is called Infrared Escape. So in this one, you play a ray of infrared light, and you're trying to dodge the greenhouse gases and escape into into space, which is the way that cooling of the planet happens. So you're doing your job as an infrared ray to escape out to space. We're collaborating with game developers in this. And if you're a game developer yourself or an artist or know people like that, a teacher, right? We would love to collaborate with you on this. Each year we host a game jam that's a virtual event that lasts anywhere between a weekend and an entire month, depending on what kind of speed you want to do. The last one of these, we had over 400 participants worldwide, and they made a total of 48 games. And I think if you check out some of these, you'll find things that are much more fun than the ones that I've shown so far. Little card games to sort of plant growth simulators, right, to clicker type games. So we would love to work with you on this. We're trying to bring scientists close together with creative types, right? Who can figure out new ways of telling these stories in a both scientifically accurate way and a fun way. Finally, just one more science story here for y'all as I wrap up. We're also doing research on accountability of the fossil fuel industry. Again, this is a time in the United States where especially fossil fuel extraction has increased quite a bit in recent years. The United States is now the #1 oil producer, but all of that CO2 is doing damage to the climate system, and you can calculate, even on particular weather events, even a single wildfire, what amount of climate damage was done by particular companies. This is research that's facilitated by data sets like the Carbon Majors data set that's tracked the emissions of the top 180 fossil fuel companies or countries, public fossil fuel companies, or private companies. And these make up 70% of fossil fuel emissions since 1970. What we did here was used that same FAIR model to study what if that emissions didn't exist, right? What if those historical emissions didn't happen? This is what they call counterfactual experiments. So it's imagining a different past and then studying what impact that would have on the future. And what we found in this was essentially that the warming effect lasts basically forever. These simulations go all the way out to 2500, and you can see that persistent amount of warming stays essentially forever, and it doesn't matter that much how much future emissions pathways, what the future emissions pathways are, even under high emissions or low emissions, it's about the same amount, largely insensitive to that. This has to do with competing feedbacks between on the carbon cycle side on one side and with the logarithmic sensitivity of radiative forcing to CO2 concentrations. So yeah, just our little contribution on this accountability question. Just to conclude here, and I'm really looking forward to our discussion next. Wildfires are increasing rapidly in the Arctic, and what happens in the Arctic doesn't stay in the Arctic. It affects climate worldwide. The Atlantic Ocean circulation affects many aspects of the climate, and does have the potential to decrease in the future, even if it hasn't decreased in the past. The recent increase in global temperature is very surprising, right? A lot of folks are studying why that is. Photovoltaic price in terms of climate solutions unlocks a lot of different futures that are much more people-powered, with electricity being generated locally. And finally, we really can think big with climate solutions. We need to have connections with folks who can imagine the future, like science fiction writers or game developers or artists, right? To connect with scientists to imagine better futures. So let's do this together. Thank you very much.
Thanks, Dargan, for this very inspiring and extremely relevant lecture in these crucial times. We will now move over, as you already anticipated, to the discussion and Q&A session. To do that, I will introduce our Director of the European Institute on Economics and the Environment, Massimo Tavoni, to kick off this session. In the meantime, please keep posting questions if you have any, so we can pick up on them after the first interventions. And yes, Massimo, please start.
Thanks, Mame, and thanks, Dargan, for the great talk. It was really inspiring, very, very clear, and thought-provoking also in some deep ways. So let me offer a comment first of all, and then also maybe a question to you if I taking advantage of the privilege as discussant. My comment regards last part of your talk, which is the area also where I mostly work on, namely on solutions. And you showed the great progress on solar PV. And the other thing that is really even more incredible, if you want, is the great progress of storing electricity through, for example, batteries. The cost and the technology is advancing beyond what we really thought could be possible in any of our scenarios, even just a few years ago. And chemical engineers are working hard to develop the latest technology, chemicals that can really store electricity. And that is really, together with PV, the game changer. However, as you obviously also slightly alluded to, the economic accounting sometimes misses out important political economy matters, and it is now a question of geopolitics. And the geopolitics is driven not by climate change, but it is indeed driven by the competitiveness of these alternative resources, these ideas of producing electricity cheap and electrifying almost everything from the way we move to the way we heat our houses and we produce goods. This is a game changer. It can leverage the digitalization transformation. It can leverage a lot of transformations which are essential. The problem that they put at risk the assets of fossil fuels for those countries who do have those assets, and they see that as a threat. And it's pretty obvious from the geopolitics that you see around the world. I mean, just open your Times every day, there's something new. But it speaks very clearly to this dichotomy of states, petrostates, or oil states, or fossil states, which are eager to exploit and go fast on exploiting resources that might at some point not be economically viable anymore. And then countries that, on the other hand, are trying to pursue this transformation through electrification and renewables. And this is a big tension, and it's a big power play. And we're seeing it, and I'm afraid we're going to see it unroll in the next at least decade before we can make that progress that is needed. When we're going to be able to meet twice the growth in annual demand of energy, which is about 2% per year, through renewables and electrification, then automatically we'll be able to squeeze out the fossil fuels. But we're not there yet, and it might take some time. But as you say, it's a giant battle, and in a way, it's also exciting to see from an energy point of view. Although it's certainly not as fast as we wished it would be when it comes to the climate. So my question is about the climate. I found really incredible to see such scenarios of short-term climate produced also by CMCC, but also the work that we have done on wildfires affecting the climate in the opposite direction by cooling it and masking essentially climate change, having such a large effect in the next few years or in the recent past. When we think about scenarios, we always think about technology, society, climate sensitivity, these kind of long-term things. But in the short run, in the next 5 years, I want to predict the extent of extreme events in Europe. And if the initialized scenarios which capture the initial condition in the oceans, do in fact predict much higher warmings, or if on the other hand, more wildfire will need more masking, or if on the other hand, something else will change in air pollution policies to unmask some of the effects of climate change, as we have seen with maritime transportation. That will have huge consequences beyond whatever we have imagined. And this is often not, actually it is not accounted in all the estimates of the impacts of climate change that we are accounting for. We look, we take the RCP-SSP's frameworks, but these are, there you see variation in very long time scales, whereas here we are talking about significant half-degree variations within a decade, which is a huge amount. Where do you see research going in this field? And how do you think, is there any opportunity for better integrating? And you already discussed a little bit the integration of emission-driven scenarios, obviously. But can we integrate more and work more together as a society, also to predict the instant climate change on everything from solar panel PV performance to the economy, accounting for the fact that there are these huge effects in the short run? Thanks.
Yeah. Thanks so much for your comments, Massimo. That brought up so many of the most important issues that I wasn't able to speak about, like batteries that have just plummeted in price as well, even more rapidly than photovoltaic. And does allow electric vehicles to become super cheap, and for grid scale storage to happen as well. And now, how to model any of this stuff? So much is not easily foreseen until it actually happens. So I think as scientists, we need to become more nimble, more able to do rapid modeling of these changes, to take into account the revolutions in energy that are happening, to take into account the political situations, right, that are maybe very much impeding certain climate targets. And I think it requires a lot of collaboration as well. Traditionally, the effort of climate, the physical climate modeling goes to a certain set of scientists, right? Maybe the impacts go to another set of scientists and the solutions go to another set, right? So it's really exciting to me to be at CMCC where these folks do work together, right? You all have your own institutes that work on these projects, intensely on your own, but do communicate well. And I think that's what we need to have happening. Is very rapid modeling capabilities that take into account all of these different aspects, right? So much is just uncertain until it happens, right? With the huge changes in transportation with COVID, for instance, and then changes in fuels of the shipping industry leading to less air pollution over the ocean. So I'm very excited, but I think we need a new framework for some of these things. That wasn't nearly sufficient to answer all of the things that you brought up, but just some thoughts, and thanks for the.
You're welcome.
Yes, thanks, Massimo and Dargan, for the question and the answer. We will now pass over to the questions from the audience. There are quite a few, but I think some of them we can combine them, so we managed to answer more or less what has been brought up. Some of them are about the relation between the CO2 emissions and the warming. So one question is what the relationship is between the quadrupling and doubling simulation with anthropogenic actions and aerosol and ocean heat. And while you elaborate on that, there's also more specific questions. If you know, what is the implied climate sensitivity in the FAIR model?
Oh, sure.
And
Yeah. Great.
a last element of this for the non-modelers in the audience. One participant was rightly wondering what you mean by initialized simulation, so why that would matter on the outcome. So maybe you can elaborate a little and clarify a little bit of that for the, as I said, for the non-modelers in the audience.
Yeah, certainly. Yeah, great questions, everybody. Thanks for these. We'll try to get to the ones later that we don't answer in the time period here too. But CO2 quadrupling and doubling, hopefully that won't occur in the future. But oftentimes with modeling, it's useful to run more extreme experiments in which we can make a really big change and study the climate response to that within the model. That it helps in terms of not having to run as many experiments. You can see the signal very clearly in that situation. So we run some of these for different reasons, basically. A lot of my early career was focused on running highly simplified setups, like running an entirely ocean-covered Earth, doing things like changing the rotation rate of the planet, changing the size of the planet, changing the moisture content of the atmosphere. And in some situations, these can help you understand smaller changes that occur in the year-to-year variability or decadal changes with global warming. And aerosols and ocean heat. A lot of these, just in terms of my own research, we were able to study that in the more idealized context first, and then apply it to more complex situations later. I'm seeing that some people have suggested some cool game ideas. We would love to communicate with y'all about that, especially during the game jam. That's a great place in which to interact with folks who are experts in game design. What's the climate sensitivity implied in the FAIR model is another great question. So there's a range, and it's not only the CO2 levels that are tuned to match observations, it's also the temperature change that matches observations. And there's a range of climate sensitivity allowed by those. Across the ensemble, it's a very wide range. It ranges from about a little below 2 degrees Celsius per doubling of CO2 up to about 5 or so. But again, that's not prescribed a priori. It comes out of the ensemble with a prior distribution that's determined by climate models. And let's see. Oh, yeah.
Initialization was the
what
other
does
point.
initialization mean? So initialized means updated to the very current conditions of the ocean, especially. Y'all maybe you're familiar with El Nino Southern Oscillation as being a big natural variability source in the ocean. It's centered right on the equator in the tropical central and eastern Pacific. But it's another one that sends out these signals of weather and climate that go all around the world and lead to shutdowns and monsoons and massive downpours and landslides and things like that, right? So if you update your forecasts continually with the new conditions of the ocean, then that is useful. There's a difference between initialized and uninitialized that gets into a little more of the technical stuff, but it's useful to have both, basically.
Thanks. Then there's another topic from the question that emerged is the solar panel discussion. Okay. So there are 2 questions related to that. One is if your applications can also help to visualize the great potential linked to an extended use of solar energy worldwide.
Right.
And still related to that and the prices and the costs that are involved. So the good news that the solar panel price is dropping, but what about the battery prices? They also would be required to drop at scale. And if it's possible to look at some of these points as well, along with the solar panel costs.
Yeah. Terrific questions, y'all. Thank you very much for these. So in terms of visualizing solar energy potential, I'd point you to the Global Solar Atlas, which is a really terrific tool that shows this all around the world what the capacity factor would be for solar panels, and it's really fun, especially in a classroom setting. It takes a little bit of work to understand what exactly is in there, but you can put in different size of solar arrays in all sorts of different places, and they visualize that well. But I think we need more creative ways of visualizing this sort of stuff as well. It's still a big old map of the world with just colors, and I think we need some way to bring that home, and visualize our local communities. So we tried to do a little bit of that with the project called The Sun Also Rises in Washington. We showed a bunch of maps and places where it's actually happening in Washington State. Again, a very gray place, but the price drop. So solar panels can be installed with or without batteries. And it's still typical for, in many situations, for them not to be installed. What I'm interested in, especially, are ways to make it affordable for everyday folks, right? It's kind of a luxury item in terms of the individual house scale still in the United States. But there's also some really interesting initiatives like community solar, where a whole group of people can invest just a small amount, and then they have that panels installed right on the rooftops, and you can get loans for things in ways that you wouldn't have otherwise been able to do. The battery is nice, but another thing with that is electric vehicles could possibly serve as backup power as well. If there's real attention taken to when charging of vehicles occurs, right? The typical electric vehicle battery in the United States, the cars now, these are about 200 kilowatt hours for a typical electric vehicle battery now in a, Tesla or, other electric vehicle manufacturer. Those have enough battery power to power an entire house for about a week. So there's a huge amount of storage that's already going to be built within vehicles alone. So if that could be leveraged better, then it wouldn't necessarily be needed to have everybody install their own battery, right? The grid would sort of evolve to have that naturally. Let's see, was the last one this one about polluters?
I would suggest to close with the one that relates to the accountability issue, which is a nice one.
Yeah.
Do you see any chance we'll find a viable way to stick the large polluters to their responsibility and make them pay the bill? At the end, this is the core reason behind COP's failures. We do not find a political viable way to do that yet. Shall we have to wait for so large disasters to move the mainstream public opinion?
Right. Yeah.
What's your take on that one?
So I think that it is possible to hold them accountable. For some of these events, like the wildfires in Los Angeles, and we had a huge heat wave in June of 2021 in Seattle. There are actually lawsuits against the fossil fuel companies because these are events that very clearly would not have happened without the changed climate. So I think it is eventually inevitable that those polluters will be held responsible for that. Now, the fossil fuel industry has a lot of political power, right? So it's tended to more be the other way. There's something called the Energy Charter Treaty, which allows fossil fuel companies to sue countries if they haven't, if they ever reduce the amount of drilling for a particular project. And I think another very big political, progress point that's been made in recent years is that the Energy Charter Treaty was rejected by a lot of European countries in recent years. So no longer will the fossil fuel company be paid if a country chooses to say no to having this huge multinational, extractive industry coming in and polluting their homes, right? So yeah, thanks everybody. I'm going to get more to on these questions right after, and we'll try to get back with y'all.
Yeah, thanks again. That was an excellent lecture, I think, and very, very inspiring, very quite a few interesting thoughts to follow up on. And I hope we managed to clarify on most of the questions that were raised. As you said, we're gonna try to go through these afterwards. And yeah, thanks for this wonderful lecture.
Thank you so much.